So when we talk about waves, again, we've been talking about light waves specifically, but now we need to talk about where light waves and electrons come together. So this is called the photoelectric effect. So it refers to the emission of electrons from metal when light shines on the metal. So metal has kind of a weird relationship with their electrons. You have all of the metal atoms in the compound or in the material, but they kind of share their electrons between all of the atoms in that material. It's actually called a sea of electrons. So the electrons are not really around a specific atom, they're just kind of hanging out around the atoms. Okay, so that actually helps with the photoelectric effect because the light has enough energy to just kind of knock some of them out. Okay, so when we also talk about this, we're talking about a quantum. So energy, a quantum is energy that is the minimum quantity of energy that can be lost or gained by an atom. Okay, so it's a quantum, it's basically a little bitty package of energy. Okay, and it's basically saying, okay, the atom, if it's going to lose energy, it's going to lose either this quantum of energy or more. Okay, or if it's going to gain energy, it can only accept this amount of energy. Okay, so that's the quantum part. All right, so looking at the photoelectric effect, you have your electromagnetic radiation, your light in this case, coming in and it strikes the metal. Okay, now this has to be a specific wavelength, specific energy, because they are related. Specific metal, different kinds of things like that. But once it hits the metal, it can actually eject some of the electrons from that metal. Now granted, this is not as difficult to do as it would be to strip an electron off of a different type of atom that's not metallic. Okay, but because metals have this kind of weird sea of electrons relationship with their electrons, you can actually knock them off relatively easily this way. So basically the light comes in, knocks some electrons off the metal, and then you get a stream of electrons coming off of the metal. Okay, and then because they have an anode, okay, in this contraption here, the electrons get attracted to the anode, and then that creates a voltage source. So if you hook it up in a cycle, you can actually have the electrons flowing from the cathode metal, or from the cathode, which is the metal plate here, towards the anode. They go down the wire and then can come back to complete the circuit. Okay, so that causes an electric current. Okay, just from hitting it with light. Okay, so it's a little bit weird, but all right. So going into energy and frequency now. So there was a German physicist named Max Planck. Okay, so yeah, he's got a weird little name there. But he proposed a relationship between a quantum of energy and the frequency of radiation. Okay, which is why you have to kind of match the wavelength energy of the light you're using to the specific material in the metal. Okay, the specific types of atoms. So this is him. Great looking guy. Okay, so he came up with this formula. E equals HV. Okay, so V is still your frequency, okay, which is in units of 1/seconds. E is the energy, okay, in joules, okay, which is the new unit. Haven't really used it yet, but J, joules. H is Planck's constant. Okay, so again, this is a constant. Okay, so it's 6.626 times 10 to the negative 34th, and that's joules seconds. So joules times seconds. Okay, V again, oops, didn't have that on there. V again is your frequency in 1/seconds. Okay, so this is relating energy specifically to your frequency. So you have a higher frequency, you're going to get more energy. Okay, you have a lower frequency and it's lower energy. All right, so if you right now go ahead and make a wave with your finger. Okay, if you make it a nice rolling wave, it has a long wavelength, low frequency, you don't really have to use a whole lot of energy to do that, okay? But then if you go back and using your finger make a wave that is like on 50 cups of espresso, you know, it's just kind of bouncing back and forth. That's a lot of energy. It's a very short wavelength, but you're using a lot of energy in that, okay? And it's a very high frequency as well. So energy and frequency kind of go together. If one of them is high, the other one will be high. If one of them is low, the other one is going to be low. And then wavelength is kind of the opposite. If energy or frequency are high, wavelength will be low, okay? And the reverse as well. All right, so now with going back into the photoelectric effect, you also have photons involved. Okay, so the photons are particles of electromagnetic radiation. They are weird. They act as both a wave and a particle, so they have kind of a duality to them, which is very strange and difficult to work with. But they don't have any mass, okay? But they do carry a quantum of energy. Okay, now the photons, again, that energy is related specifically to the wavelength and to the frequency of the electromagnetic radiation that it's a part of. Okay, so that's where that quantum of energy comes from. Now the energy of a photon, again, like I just said, depends on the frequency of the radiation. Also depends on the wavelength, so on and so forth, because they're all interconnected. Okay, so you can also say the energy of a photon is equal to Planck's constant times the frequency of that radiation. Okay. Now, when we talk about one photon hitting an electron, okay, that's what we're going into right now, because that is the heart of what's happening in the photoelectric effect, is you have a photon with a quantum of energy hitting an atom. Okay, hitting an electron, something in that atom, right? So talking about this, we have electrons in their ground state on these atoms. That is the lowest energy state of an electron. It's where they're happiest, okay? They don't have too much energy, so they're not trying to fly off the atom, and they don't have too little energy where they can't do anything. Okay, so the ground state is where they're happy, they're moving around the atom, just hanging out, being chill, okay? You also have an excited state, okay? So again, think if you have this electron, think of it like a toddler, okay? If it's just kind of, you know, it just woke up from a nap, it's doing its thing, not super hyper, not really like, you know, waking up, but still not really all that tired anymore, okay? Then you also have an excited state. So you can think of that as if that toddler were given espresso and a puppy, okay? Bouncing all over the place, right? So that's kind of the idea with excited state electrons. These electrons have higher energy, okay, than their ground state. So they will actually jump up to a higher orbital, which we're going to get into in a little bit. Basically, their ground state orbital, where they generally hang out, is too kind of laid back and relaxed to handle them in this excited state. So they have to jump somewhere else that can actually handle that level of energy. And it can actually, the electron can jump between those two states relatively well, okay? But in order to jump from a higher state to a lower state, it actually has to release that energy. It has to actually get rid of it because that's not accepted in its ground state. Okay, so now we get into the Bohr model. So Niels Bohr proposed a model of an atom that actually links the atom's electron to photoemission. Okay, so this is the planetary model. It's got your nucleus right in the center, and then it's got your electrons moving in defined paths around the nucleus. Okay, so those are called orbits. All right, so we're going to get really familiar with some orbits here in a little bit, okay? Now the energy of these electrons is higher when the electron in orbits, or when an electron is in an orbit that is further from the nucleus. Okay, so their ground state is closer to the nucleus, But if they get enough energy, they absorb enough energy that they can jump to an outer energy level, an outer orbit, that's where they have that higher energy. Okay, so that energy is kind of like the toll price that the electron has to pay to get into the higher energy level. But if it loses that extra energy, which it eventually does want to, it'll have to go back down to its ground state, to its lower level energy. So energy has to be added to an atom in order to move an electron to a higher energy level. And that energy is actually moved around and transported by photons. So if an atom absorbs a photon, it's not absorbing mass, but it is absorbing energy. That energy gets put where it can actually be held on an electron. So that electron will jump to a higher energy level. Once it kind of gets up to that higher energy level, it pretty much immediately regrets its decision. So it releases energy, again, in the form of a photon. And then it falls to a lower energy level. It falls back where it was. So the energy difference between these orbitals is very specific. If you're going from, say, the 5th orbital out to the 2nd orbital from the nucleus, okay, that's going to have a very specific amount of energy. Now, the energy relates directly to the frequency of that photon, and that frequency relates directly to wavelength. Now, wavelength is actually what we're seeing when we see color, okay? So the energy relates directly to the color of the photon, or the type of electromagnetic radiation that's released. So if that photon has a wavelength that's within the visible light spectrum, you will see it as a very specific color, okay? So this is how we get fireworks, actually. It's because you are basically increasing the energy level in electrons in those atoms, and then they regret that decision. They release the energy. They fall back down to a lower energy level, and they release photons with specific energy levels, okay? And that creates the color that you see in fireworks. So each photon that is emitted from these excited electrons, these excited atoms, carries that very specific quantum of energy, okay, which again relates directly to its wavelength or the color of the light. Okay, so this is kind of showing how this works. You have a photon that comes in, okay, and it hits an electron. Now that electron absorbs that photon, and it had enough energy that it can jump this electron from the first energy orbital, or energy level, the first orbital, all the way up to the 3rd, okay? So it jumps it all the way up here. So this is a much higher energy level, needs a lot more energy to stay here, so it regrets that and decides to release a photon, okay? Oh, wait, actually these are two different things, sorry. So this photon comes in, it's an orange light, and that wavelength has enough energy to jump this electron from the first energy level up to the 2nd, okay? Now, in order to jump back down to the first, it's going to have to release this photon, this energy, this excess energy that it absorbed. Over here, we see that emission process, but instead of being in the 2nd energy level, it's now in the 3rd. Okay, so maybe it absorbed another photon and jumped up to the 3rd. Okay, so now it's going to release all of that excess energy to jump back down to its ground state in E1. Okay, so when it releases all of that energy, you have a photon that comes out that has the specific energy to produce this green light. Okay, and that's how you get that flash of color. So I actually have a demonstration that we'll do pretty soon on this concept. But that is the end for this section.